All right, so let's get back to the lecture then. We started talking about convolutional neural networks in our last lecture, and specifically we discussed some different types of layers, specifically the convolution that we talked in detail, and also fully connected layers. So we've defined two types of layers thus far: fully connected and convolutional. Convolutional layers means nothing else than applying a linear filter, typically, to the image. So if you have an image here, same idea can be applied to a sound wave, for example, which would just be one dimension instead of two. And then you have a filter, let's call it F, right? Then you want to apply this filter to every possible location in your image, right? And if you've taken image processing, you know how to do that. If not, you can watch the video lectures, although image processing is a prerequisite for this course, so you probably have taken it. So this is nothing else than doing a convolution, right? So I have my image here, and I have my window where I apply my filter, and this gives me just one value, right? The value of that convolution. If I do this for not just one filter, but instead for a variety of filters, right? Every time I apply this filter to the image, I obtain another image, right? So for every location of the filter, I obtain a result, right? That corresponds to the center pixel in the original image, right? You know all this from image processing. So you generate output 1, and if you use different filters, you could get output k that correspond to the different types of filters that you may use. And this is typically represented with a tensor. Again, this is something that we did cover in detail in image processing. So you end up with this tensor, right? It's a 3D tensor, or tensor of order 3. That is nothing else than all the different convolutions that you have done, right? So each slide here corresponds to one of these convolutions, right? Okay? All right. If I go too fast, stop me, because I'm going to try to get us to the end of the lecture today, and there's a lot to cover. So these filters, general, let's call them Fj, are given by also some parameters, right? So this is a mapping function, as always, mapping function of our input data and some parameters that I specify, and those are the ones that specify the filter. Now, the way to do that is, obviously, the correct way to do that is by using the FFT, the fast Fourier transform, right? So where you convert, remember, both the image and the filter to the Fourier domain, right? And then the convolution just becomes a product, right? And you can very quickly compute these things. Now, interestingly, this is not how most people do it, which begs the question why, but just people usually don't do that. And many of the softwares that you will see out there actually implement these convolutions as a correlation instead, to make it run a little faster than a convolution in the original space. But even in that case, the problem that you have, if you do it that way, because remember, if I use the Fourier domain, anyone can tell me what happens when I convert this into the Fourier domain? Right, and what else? But there is something else that I assume about this function. It's periodic, very good, right? So this is a periodic function, right? And that means that I don't lose any information from that function because this function repeats in every direction to infinity, right? But when I apply an actual convolution or a correlation to the image, then I need to locate the window of the filter at every location, right, at every pixel. The problem is the pixel right here, right, the very first pixel, would have a window that goes outside the image domain. And how do I solve this? And the way people solve it, if you want to actually do the actual convolution in the original domain, the image domain, is to add a frame here, okay? Typically with all zeros, although there is no reason why you should add zeros, you could again just copy the image, right? Extend the image like the Fourier does. And they call this padding. Actually, people call it also zero padding because you add zeros, right, in that padding. And if you want to use those softwares that use the correlation to compute the convolution instead of the FFT, then you have to add the zero padding, right? You have no choice. Otherwise, every time that you apply a convolution, you would lose half the size of the filter, right? So you'd be able to do convolution in here. So you go from n by n to now a result that is n minus 1/2 of the size of the window, say W, right? You see how this goes? And same thing here, right? And obviously, eventually, once you start doing convolutions, and in a typically deep convolutional neural network, you do many of these convolutions, right? Many, many of them. You end up with nothing, right? You just eliminate all the information, all the resolution. So you want to make sure that you maintain the resolution. So make sure that you know, that you see, that you understand how you add paddings with these softwares that you can use. All right. There's another interesting fact, which is, as I said, all this is linear filters, right? So all that I'm doing here is applying linear filters. Now, a linear filter, obviously, is going to be nothing else than, so theta is going to be my vector W and my bias, right? So I'm going to do X transpose W plus B, right, for example, right? So, but why? Why use a linear function as your filter, right? You could use nonlinear equations, right? You could use nonlinear functions to do the mapping. So you could do, for example, the sum of W1I xi plus W2I xi, say xi minus 1, plus W3I xi plus 1, and so on, right? Maybe another term could be Wji, could be xi squared, right? And so on. To my knowledge, no one has done this in convolutional neural networks. I just don't understand why people don't try more complex convolutions. So that's something you may want to try, right? Especially in your project, your final project that's in Canvas. All right, any questions about this? Question.
How do you decide which frequencies in the Fourier domain to measure the property?
Right, so there are two solutions. The preferred solution is you decide. You try, and whatever works in your problem. I know. Yeah, you're going to have that reaction, you're going to have it a lot in the next 3 days. I can assure you. I mean, this is deep learning. Deep learning is you just try and see what works and what doesn't, right? So that's why experience is so important in deep learning, because only through experience you learn what works and what doesn't, right? There is no manual on how to drive this car. And it's a very complicated car to drive. It has a lot of parameters, right? So that's one way. Another thing that you could try is you could put as many of those parameters as you can within the training parameters and then use them in backpropagation to try to learn which are the frequencies, the derivatives of the filter or what have you, right, that are relevant for that. The phases, the size. The problem with that, as we will see today, is that learning in deep networks is really hard. Backpropagation is not the panacea, right? I mean, it's not going to solve all your problems. So the more parameters that you have, the more difficult it is to learn. So, yeah. Learning in deep networks is really hard. We'll get to that. And usually it requires a lot of manual help. Yes, question?
Do we prefer the smaller filter or larger filter? Or
Again, it depends, right. So the question is, do you prefer smaller filters or larger filters? It depends on the problem, right? So it depends on what your problem is. You will want to use smaller filters or larger filters. If, say, your problem is face recognition, but you know that in your application, the subject that you're trying to recognize is right there by the camera, right? You're gonna be using a certain number, certain size of filters, certain orientations of filters that are different if you're trying to detect faces in a football stadium, right? Where faces may be 5 or 2 by 3 pixels, right? Whatever they are. You see what I'm saying? So obviously it's totally tailored to every specific application. And don't get me wrong, these networks, as I said already several times, do amazing things, right? They work really well when they work. But when you read in the news, you know, machines are about to be as intelligent as humans, and soon they will surpass humans in intelligence. Like, whoa, 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 whoa. These networks have to be specifically designed for every single problem with all these parameters that we're discussing, with all these other things that we're talking about here. So, you know, there is a long way until we can say, oh yeah, these are the parameters that will work for every problem. That's just not there yet. All right, so another type, is there another question? Okay, another type of layers, of types of layers, other than the convolution and the fully connected that we've seen, is the pooling layer. Now, what's a pooling layer? Again, as I already said, one of the problems that we will see today is that learning in deep networks is really hard. Because remember, backpropagation, what is backpropagation? Backpropagation is nothing else than what we have been doing. If you're using the square laws, it's least squares, right? Right? Nonlinear least squares. And if you're using another laws, it's just gradient descent. So if you have here your parameters, actually let me call these parameters theta, right? And your result of the loss that you want to minimize, right? And you start at some location, say here, then you follow the direction of the gradient of that loss, right? Of that loss function. You follow the direction of the gradient until you get to a minimum, right? That is basic gradient descent, which is what backpropagation uses. Only the idea of backpropagation is you apply the chain rule through the embedding of functions that we have, so we can actually get the parameters at every single stage of that embedding, right? Of that embedding that we saw, that was f of f of f, right? Oh, actually, to be precise, it's f of x theta 1, and then I do f of this theta 2, and then f of this theta 3, and so on, right? So I keep going this direction. So by applying the chain rule, then I can optimize all the parameters, right? This is very nice. This very easily, is easier said than done, because again, the size of these things grow exponentially, right? They keep growing and growing and growing, and finding this, being able to find this minima becomes increasingly difficult. So one solution that people have found to actually work in practice is adding what's called pooling layers. And what pooling layer is, it's a reduction of the dimensionality of the parameters that you have at that moment, right? Or the representation, rather, that you have. So remember that in deep networks, you start with, say, a layer, right? Layer 1 here, that has a certain number of nodes in your graph. And then you move to some other layer by layer K that has a certain number of nodes, and so on, right? So what it turns out that it's useful to do compression once in a while, right? So you're going to end up with a layer at layer, say, Q, where the number of nodes here may be approximately the same number of nodes here, but this is larger than the number of nodes here, right? Right? Okay. And this is called pooling. And there is, again, no manual about how to design a pooling layer. You could apply PCA, right? PCA, it's a well-known technique to reduce the dimensionality of your data. You could apply ICA. You could apply any of the feature extraction, feature selection methods that we've defined. Add the boost for feature selection, for example, anything you want. The most common one that people use, it's called max pooling. And in max pooling, this is the simplest maybe algorithm that you can imagine. But the idea is that you just take the maximum of the maximum value within a window, right? So for example, if I have, say, a 4x4 image, okay, so I have a 4x4 image like this. And what I mean by a 4x4 image like this is that I started with my original image, right? And from here, I went into a tensor representation and then to another tensor, right? So now I can apply filters here in that tensor and get another convolutional layer and then another convolutional layer and so on. You see how this goes? And it gets to a point that it's a slice of that tensor, say it's of this size. And now I decide that I'm going to take window sizes here of, which actually I made it 3x3, okay, of size 2, right? So I'm going to take these 4 windows. I'm not overlapping this time. I'm just taking non-overlapping windows here. And then if I have, say, 6, 1, 3, 2, 1, 1, 0, 5, 4, 6, 6, 5, 0, 0, 1, 7, right? Now from this first window, so I have 4 windows, right? So I'm going to end up with a 2x2 image here, or matrix. So from this one, I'm going to take the maximum. What's the maximum? 6. What's the maximum here? What's the maximum here? And here? 7. And that's my output, right? That's max pooling, just taking the maximum. It's silly, but people found out that tends to work in practice. Nobody knows why. It just does. Okay. Now, again, you can use all the sophisticated methods that we have presented here. Now, nothing is stopping you from doing that. Now, at the end of the network, when you get toward the end, So you may have here some convolutional layers, right? So let me do it this way. Maybe you start here with your input, and you pass your input through a convolutional layer, and then maybe you do some other convolutional layer, and then maybe you do some max pooling, and so on, right? And as you get toward the end, it's typical to have fully connected layers. Or I should say, it used to be very typical. It's less and less typical now. Actually, of the latest architectures that we will see next week, people have started using less and less fully connected layers, right? Fully connected layers have almost disappeared from the top architectures right now. But fully connected layers tended to be, and still are in many architectures, at the end of the network, okay? So the idea is that here in these first and intermediate layers, you do more local processing. So imagine that you have an image or a piece of sound, a one-dimensional wave, and you do local processing in these signals, right? And then at the end, you want to combine all this local processing into an outcome, right? Either a regression or a classification. I'll post in Canvas also a nice demo that someone did online that allows you to see how these things, for very, very, very tiny networks, but how these things behave in real time, right? You can actually see their behavior. It's pretty cool. Okay, any questions? All right, so let's talk about training these things, okay? How are we going to go about training these networks? So, imagine, and we'll talk again next week about different architectures that are out there that you can use. Imagine that you already have an architecture. By an architecture, I mean a sequence of layers, right? That I have decided they have these certain convolutions, a certain these certain pooling layers, is certain fully connected, and so on. And now my question is, how am I going to train that? And the obvious answer is, well, you're going to use backpropagation, right? Well, hold on a second. We have already discussed in quite detail in this class, in this course rather, two basic methods to do training with gradient descent. One is a stochastic gradient descent, remember, where we take every sample at a time, or one sample at a time, right? And we apply gradient descent to that one sample, and then you take another sample, and we apply gradient descent to that sample. And the other one that we discussed was, anyone remembers? No? No one? The batch algorithm, right? Where you take a set of, or all of your training samples at the same time, and you compute the gradient for that set, and then you run it through gradient descent, right? So let's review these two, because these are two methods that we can use here. So this is very broadly, but broadly speaking, we will differentiate between stochastic gradient descent and batch. So in a stochastic gradient descent, we have wk plus 1, meaning at iteration k plus 1. My parameters w, right, my weights. By w, remember, usually I mean the weights in that network, right, or the parameters in that network. Are equal to wk minus some alpha, maybe let's call it alpha k, the gradient of my function f s sub I wk. Now here I say s sub I indicating the underlying distribution, okay, of that specific sample, where again wk represents the value of our parameters at time k, or iteration k. People also call it epoch. Si is my pair that defines my distribution, xi, yi, right? My training pair. Xi, it's the input, yi is the output. And f is the objective function, right? Whatever I want to use as a loss function. Now, this is to be contrasted with batch. In batch, what we do is our wk plus 1 is going to be equal to wk minus alpha k, the gradient of Rn wk. And anyone can remind me of what Rn is? We've seen this many times. This is the empirical error, right? So this is the empirical error, which I can compute as 1 over n, the sum over all I of the gradient of f si wk, right? Now, there's a very interesting parameter here that we'll talk quite a bit today, which is this alpha. And remember that we had discussed this when we talk especially about linear classifiers. We talk about this alpha. And this is the parameter that determines my learning rate, right? And the importance that I give to the gradient descent. And when we talk about linear classifiers, I spend quite some time on this. We're going to discuss how to set that alpha, right? What are the values of alpha that I really want to use to try to make this this backpropagation work? Okay, so which of these two do you prefer? You can use both, right? No one's going to stop you from using one or the other. You could try both, see what works, given your data. Now, stochastic methods are generally preferred. You generally prefer stochastic methods. There are two reasons for that. Stochastic methods are much less computationally expensive. I only use one sample at a time. So obviously, I'm saving a lot of computations. And also, if I have an optimized learning rate, alpha, they are found to converge faster to the solution in practice. Okay. Now, theoretically, and I say theoretically, batch methods are better because batch method is known to converge for what's so-called a strongly convex functions. Okay, it's known to converge fast for strongly convex functions. Of course, our function is not going to be strongly convex, so we probably don't care about that fact. Although batch algorithms, it has to be said, have a lot of theoretical backing behind them. So they may be appropriate. One thing that you can do, that you should do, is to compute the rate of convergence. And how are you going to compute the rate of convergence of these things? One way to do that is to is to compute the expected value, right, of RnWk, which is your empirical error that I just mentioned in there, minus Rn star. And then remember that this star means the minimal of your function, aka your solution, right? And we know that for stochastic methods, for stochastic algorithms, this is approximately or equal to, let me say, this is equal to the order of 1 over k. Now, you have to assume a couple of things for that the function is strictly convex, okay? It's convex at every point, and that the way that you draw samples at every iteration from your training set is done uniformly across the sample set that you have, okay? Okay. Now, as you can imagine, there is a third method that you can use, which is the one that most people use these days. Anyone can, even if you don't know, anyone can make a guess of what that will be.
Randomly select a batch, a small batch.
Right, so it's going to be a combination of these two, right? I'm going to try to find a midway solution, so to speak, between these two. Middle of the road, if you will. And this is called mini batch. And here you select a subset of samples. Let's call it capital S sub k, which correspond to, say, xi, yi, all the way to x. Actually, we want to say I1 here, IR here, make it easier, notation-wise. And now I can compute my new weights at time k plus 1 as the weights at time k minus the same I had there, the learning rate alpha k divided by, now there I had in the batch I had divided by the number of samples n, right? Here I'm going to do the size of my mini batch, right? So the number of elements in sk. And then the rest is obviously the same. For all the elements in sk, I'm going to compute the gradient f si wk, right? Yep. All right. Another thing that you want to do, and you certainly want to do that, and for your homework or project, rather, I think you can probably try all three of them and see how they work. If you only want to do one, you're running out of time, you just want to do one, I think your data sets are small enough that you can do a batch and be done with it. Or just do a stochastic if you want, right? I don't think it makes much sense to do mini batch for the smaller data sets that you have in your project. But if you have larger data sets, you would prefer to use mini batch, okay? But another thing that you must, this is a must, that you must do is to pre-process your data. And if you don't do that, I guarantee you that you are not going to learn anything. Now, if you've taken, again, image processing with me, you know how important it is to normalize the data whenever you run algorithms, because otherwise you soon enough get outside the range of numbers that you can represent correctly in a computer. Either they go too large, or the decimal precision that you have is not sufficient to represent your numbers, and then you just go into not a number or zero, right? But either case, it's equally bad. Now, how are you going to normalize this? You could use PCA. So one solution would be to use PCA, represent the data in the PCA space. That works actually relatively okay. Even better, maybe do whitening. This will uncorrelate your data, or any way of uncorrelating your data will work fine. But try to uncorrelate the data as much as you can. I would probably suggest whitening as a good way to do that. Certainly, you want to mean normalize the data, right? And those are things that are given by these transformations, right? But if you don't do PCA or whitening, certainly mean normalize your data, right? So compute the mean, subtract the mean from every sample, and normalize the variance. So again, this would be xi minus the mean of all samples, and that would be, so if I call this xi hat, for example, that would be xi hat divided by maybe the square of the variance, right? Okay. Now again, PCA whitening will do that for you, but at the minimum, if you don't do that, do this. Okay, so going back to, oh, shoot, I erased that, didn't I? Okay. Let me draw that again. Now remember that I had a network here. So I have my input X, right? And then I send this through a layer that's maybe a convolution. Maybe I have another convolution here. Maybe I have a max pooling here, right? And so on. And I have a fully connected layer, and I have my output here, right? At certain stages, right, you want to add, remember, a non-linear mapping, right? A non-linear function. So you're going to add a function g, let's say, right? That non-linearly maps your, doesn't make sense. That's going to non-linearly map your data, right? Because otherwise, remember that the classifier that we have decided to use, it's a base linear classifier, right? Which is W transpose X, or X transpose W plus B, right? And yeah, sure, that's the basic base linear classifier, but it's linear, right? That's not going to be very good in most of my applications. So once in a while, I'm going to add this nonlinear mappings. And one of them that we have discussed as a possible function to use, sometimes you'll see this called activation functions. Is the logistic sigmoidal regression function, right? Logistic sigmoidal, which is given by 1 over 1 plus e to the power of minus x. And it looks something like this. And the thing about this function is that after some value, say negative t, f of x, so sigma of negative t, in that case, it'll be approximately 0, very close to 0. And the same after this, plus t, right? Here, f of t will be approximately constant, right? It will saturate at some value, right? Two problems with this function. So this function was the classical function that neural networks used in the 70s, 80s, 90s, maybe early 2000s, certainly 70s and 80s and early 90s. There was a preferred function, but it doesn't work too well. And the reason is, well, there are several reasons. First of all, this is not mean-centered, right? So it never passes through 0. And that obviously has a problem because where you're going to end up once you compute the derivatives of this function is that you're always going to have either positive numbers or negative numbers. You're never going to have a combination of the two, right? So if I were to draw space here, right, of all the possible outcomes, I might have this is positive and this is negative. I might have any value here, but I can never be in any of these other quadrants, right? And that numerical is going to cause me problems when I try to do gradient descent. But the other problem is that when I compute the derivative for values that are smaller than negative t or larger than positive t, then that gradient is going to be 0. So I'm doing nothing, right? The backpropagation algorithm is stuck, doesn't know what to do, unless I have infinite precision, remember, right, to represent really, really tiny numbers. So an alternative to this is to use the 10H that I've been talking about. So instead of using the sigmoidal, I would say always avoid the sigmoidal function unless you're desperate and you want to try it, just in case, but like a last resort. You never know. It may be the best one, but if I were you, it would be the very last one I try. So the 10H, remember, looks something like this, which has an advantage that it goes through 0. So it looks something like this, right? Correct? And that's an advantage because you will be able to search for the gradient across all quadrants, right? So facilitate convergence, but it still has the problem that after a certain value here, q, right, and negative q, this is almost constant, so the derivative is going to be 0, which means that I'm going to stop learning as well, right? So it's also a problem. It's not as problematic as a sigmoidal, but it's still problematic. There is a type of architecture of networks that we're going to discuss next week, or the week after, in our final week, which are called GANs, as generative adversarial networks. We'll get to that. That actually use the 10H, but it's basically the only one that is still using the 10H. Most networks use ReLU. Now, remember, this means rectified linear unit. And the rectified linear unit looks something like this. It's 0 here, and then at this point it becomes x equals y. So my function f of x, it's the maximum between 0 and x, right? Simple as that. This has an advantage, which is that it doesn't have this problem of the gradient of x turning or becoming 0, because it never saturates, right? It continues growing. So as long as you normalize things properly and you don't run out of possible numbers to represent, then that works better. Still, is 0 here, which obviously means that in that space that we had, where I'm going to be looking for my gradient, right? I can only represent gradients that are in this quadrant, right? I don't represent anything in the negative space because I can never have negative numbers, right? So I always have positive gradients. Which means, this is important, which means that if you're going to use ReLU, and I suggest that you start by using ReLU. ReLU should be like your first choice, right? And if that doesn't work, then you try something else. So start with ReLU. But if you use ReLU, you need to initialize your parameters. And how are you going to initialize your parameters? Anyone? Your parameters must be initialized to, what's that? All positive numbers, right? All your parameters have to be positive, because if you initialize your parameters here, good luck, right? How are you ever going to get there? I mean, you tell me this is 0. The derivative here is 0. You're never going to get there, right? You have to initialize your parameters in the positive quadrant. Be very careful, because otherwise you're going like, Aleix told us to use ReLU, but that never converges. Well, yeah, it's the initialization problem. Okay. An alternative, remember that we did discuss of ReLU, is to actually add a small, if you want to solve this problem, a small function here, right? So you would have something of the form max of maybe 0 plus some function h, right? Comma, or maybe some epsilon if you prefer, comma x, right? Instead of this. Again, this can be epsilon, can be a function of x or of something else. A typical one, which is called leaky ReLU, uses a multiplier, so it'd be the max of alpha x comma x for a very small alpha, okay? And this is called leaky ReLU. And just select a very small alpha, for example, let's say something like 0.01 or even smaller. I would say try ReLU first, initializing your parameters always as positive numbers, obviously. If that doesn't work, then try this. How am I going to select alpha? Try different values for alpha, small values. If that doesn't work, put alpha in your parameter space and backpropagate that alpha. See if that helps. If that doesn't help, try different functions here, right, that you can come up with that you can optimize in your backpropagation. And if that still doesn't work, then try 10H. And if that doesn't work, then before you move on, maybe you want to try sigmoidal the logistics in modal function, but at that point, we're pretty much out of options, okay? Now, there are alternatives that have been proposed in the literature. There's another one that's called something like Max Relvo or something like that. I forget the name. I think it's called Max Relvo, this one that I have noted here. But anyways, many of these variants come out every year, right? So just check the literature. What's the latest loss function? I could plug it in here. And if Relvo or liquid Relvo don't work, then you may want to try these newer ones. But don't expect to get much better results or very different results from those. Okay, so now let's see how we can put all this together to see if we can train networks. And I want to clarify here that the very first thing that we need is we need to babysit those the training that we're going to do. Okay, so it's not a matter that you just try different loss functions or you try different preprocessing normalization procedures and you let it run and hope for the best, right? It's not going to work. You need to sit in front of the computer and see how the training goes, okay? And you have to babysit it like a baby, really newborn, and give it everything that it needs, because the problem is if your network is small, you can train it very easily. But when these networks grow in size, right, you can keep adding layers like this, like what we have here, right? You can keep adding layer after layer after layer. The number of parameters grows to a very, very large. I mean, it could grow exponentially if you start putting in especially fully connected layers, right? And you could end up with millions, actually dozens of millions, hundreds of millions, and even billions of parameters. And that's where the problem really is. You have 1 billion parameters, and you have to estimate all these numbers. Good luck, right? It's very hard. It's a very difficult problem. All right. So one thing that we want to do, let me see. One thing that we certainly want to do is to add yet another help to our training process. That's called batch normalization. So let me do that quickly. I would say that this is almost a must. If you don't have that, this is not going to work. So here's what's going to happen, right? What's going to happen is that it is very convenient to keep making these networks larger and larger. By the way, I have to say that in general, and obviously that's always in general, but in general, the deeper the network, right, the deeper the embedding of functions that I have, meaning the more layers that I add, the better the networks tend to perform, okay? If you have access to very large training data sets, that's a given. But then what happens is that when you run gradient descent on the first layer, right, you end up with smaller increments on the next layer, and the smaller increments on the next layer, and yet the smaller increments, and yet smaller, right? And it gets to a point where you're just not doing any increments, right, by applying the chain rule. So what you need to do is to insert here batch normalization stages, where you renormalize your data, right, at these intermediate steps. And as before, the classical normalization is to normalize with such as your internal representation defines a Gaussian distribution, right? So let's say that x hat k, it's the representation that I have here at the kth layer, right? And what I'm going to do, I'm going to subtract the mean, the expected value of this, and I'm going to divide this by the variance of this, right, of the representation at this case. Maybe a square root, maybe, of that. Again, there are multiple ways to do batch normalization. This is the one I probably recommend as the simplest one. If that doesn't help a lot, then try other ones. There are many ones that are implemented in the software, PyTorch or whatever software that you're using for deep networks, okay? And then what you have to decide is where am I going to add this batch normalization here, right? So, okay, I lost one of them. Oh, here you are. So am I going to add batch normalization here after convolution? Am I going to add it here? And one really obvious way is to add batch normalization after a fully connected layer. This is common practice. So you may have a convolution, there may be a convolution, then a fully connected, then a max pooling, and so after the fully connected, you may want to add a batch normalization, okay? And after the batch normalization, then it is common to add a bias to your data so that this output at, actually I call it xk, right? So at this new output, xk is going to be equal to gamma k xk minus 1 plus some beta k, okay? So that you're actually adding a bias term to the output. And that seems to help as well. Now, the problem that you're going to have is that if you add this batch normalization during training, that will facilitate your training process. But what happens in testing, right? What are you going to do in testing? So there's no easy solution to that either, but what people typically do is they use the average batch normalization of all the training. That's the most typical one. And there are variants for that as well, right? Again, try different things, right? So remember, if you have a large data set, most people will use mini batch. So it means that you take the average batch normalization of all the mini batches, right? That's what you use for testing. All right, and this is all the help or the major components of the help that you can add to the network to help you learn, okay? These are the different things that people have found out that tend to help with training. Now, could you train a network without these helps, with these aids? I doubt you can do it without the preprocessing. I really do. The activation function, I mean, you have some leverage there to try different things. Batch normalization, it's not a must, but it certainly does help, especially the larger the network. So certainly do preprocessing. If you have a large network, certainly add batch normalization. And as much as you can, try to use ReLU or liquid ReLU or a variant of that, if you can. And if not, try to use 10H. And now you're ready to sit down and babysit the training process, okay? And now you need to, there was a question earlier, you need to set up a lot of parameters, right, that we have defined here. So to do that, what am I going to do? The very first thing that you may think is, all right, I have my network, I have designed or downloaded the already designed network that has preprocessing, has batch normalization, uses ReLU, what have you. And now I have also my training data, and I'm just going to apply my training data to that network, see what happens, right? Don't. It's not going to work. So what you do is you take a small portion, really small portion of your training data, and you apply it to the network, okay? And very slowly you see what happens, and you see whether you can train that network. You may be training it to nonsensical results or outputs. It doesn't matter, but can you train it, right? That's the very first thing. And once you have done this, then start increasing your training set, your training subset, slowly, one step at a time, until you're sure that you have set out the correct preprocessing, the correct batch normalization, the correct activation function that allows you to learn. If you can't, right, at one point you're finding that you're reaching a point where you can no longer train correctly, then go back to the last point that you could, start modifying these parameters, make sure that modifying all these things still allows you to train, and then try again to increase the training size, right? And then keep going back and forth until you can go forward to the very end when you're using all the training data. Okay. Regularization. You must use regularization in your loss function, okay? Now, how much of a regularizer are you going to use in your loss function? Now, remember that we discussed this in regression, we discussed this in classification, and now we discussed this in deep networks the other day when I was introducing deep networks, right? Your loss function is going to have your basic loss function plus a regularizer and, right, the regularization term. Start with probably very small when you start trying to train the network with a small data set. Start with the smallest regularizer that you can. And then as you see that the network learns, try to increase the regularizer bit by bit. But at the end, you want to have a decent sized regularizer. Because if you don't regularize these networks with 1 billion parameters, it just ain't going to work, right? You just need to regularize. And how are you going to visualize all these things? So let's see that. So what I want to do is to visualize these things in real time, if I can, so that I can see what's happening. And we have already seen that. We have already discussed how to do that. So we are going to plot here the different functions. So this is going to be the time, right? Time, or as I said, people call it the epoch, right? The step of your training, and this is your error. Right? The error function that you want to minimize, right? Which depends on the loss function that you select. If it's a square loss, or if it's the hinge loss, or whatever you're using. Okay, so we know what we want, right? We want something like this. Or maybe we want something like this, but we certainly want a function that decreases over time and decreases relatively fast, right? That's what we want. We would be okay if we saw a function that looks maybe something like this. Okay, so that's our ideal. This is what we are okay with, right? With a function that decreases slowly or slower, but that it decreases at a relatively exponential rate, or somewhat exponential rate. Now, if you said, remember that parameter that we discussed, alpha k, which is the training rate? Now, if I want to go fast, right, to reach this, and that means I have my training rate to a very high number, this is what you're going to see. Okay? It's going to start decreasing really fast, and then after a very short number of epochs, it's going to increase like crazy. You're just moving too fast, right? The gradient is the function of the error is not is more steep than what the step that you're making. So you're just jumping ahead, right? Too much, too far away. So you certainly don't want that, but this is a good indicator that you have too large a training rate, right? And that you need to decrease it. Now, on the other hand, if I have a really low, so this is high, if I have a really low training rate, I'm going to end up with something like this. This is a low training rate, right? And these two, when you start training, right, when you babysit the network, the training process of the network, you should practice with high and lows to see whether this is happening, right? With low, is it learning? Yeah, but very slow. But is it learning? Yes, okay, good. Now, if I increase it too much, is it not learning anymore, right? It's jumping very quickly to high numbers. Yes, okay. So now you know that you need to find a value in between, right? These two. And with a relatively good value, you will probably be able to get something that looks like this, right? Or maybe like this. So what are these good values? I cannot help you very much. I would say maybe on the small size, you may want to try 10 to the negative 3 or 10 to the negative 5, right? But again, I mean, depends on the network, it depends on the number of things. On the maybe even 10 to the negative 7, actually. Here, you may try 10 to the negative 3 to 10 to the negative 1, right? And see what happens. Some people, what they do is they'll do a, say, 10 to the negative 3 and multiply this by alpha, and then modify alpha, right, as a constant. So this is a constant. And just modify the value. That's an option. It's up to you, right? Guess you can make it a real number as well. one more thing about this. Now, everything I said is very idealistic. In practice, what you will really see is the following. You will see that your function decreases maybe like this, and then it stagnates, right? It just stops learning after a while. What that means is that the learning rate that you are using is working, right? It was working for a while, but after a while, that learning rate is no longer good. And now you need to increase it or decrease it, right? And once you change it, it will learn a little more, and then you change it again and learn a little more, and then again, and so on, right? And you keep changing the learning rate. And you can actually even implement this automatically, right? You can say that the training rate is a function of your error rate, right? And as your error rate decreases, right, you want to tighten the knot of the training rate. You want to reduce the value. So you adapt less and less. You just try to grind your way down that function, okay? Now, the question that really comes to mind when we talk about this, and this is a key point to understand deep networks, is why is learning even possible in deep networks? This is what people have called the unreasonable, what's the right sentence I'm looking for? I'm paraphrasing, but the unreasonable good performance of deep networks, right? What's that?
Effectiveness.
The effectiveness, if you will. I mean, think about it. It's true. These networks are very difficult to design, very difficult to train. But if you achieve that, then they work really well in some problems. Why? Why is that even possible, right? And remember, yeah, we have to solve all these problems. But if we are able to solve all these problems and we can learn, then they may actually work well in my problem. Why? Why does this happen? And the reason is that in machine learning, we were accustomed to visualizing the error rate like this, right? Because guess what? We live in three-dimensional space, and that's all we can understand, right? I mean, imagine that you were a creature that lived in a one-dimensional space, and here I come, and I try to teach you what 2D space is. How are you even going to understand what 2D space is if you've lived in 1D all your life? So now in 1D, which is the case that we drew there, this is what happens. In 1D, I have my error function here, right? That's a function of my x. And I know that my error function looks something like this, maybe. Maybe if it continues, maybe I have something like this, right? And I say, well, if I initialize my parameters here, I end up in that minimum. If I initialize them here, I end up in that minimum, right? Because all I can do is to find the local minimum where the gradient points to from the area that I start, right? Because if I go beyond this, the gradient is pointing in this direction, I can never get out of that minimum, right? But deep networks somehow seem to be able to find a much lower minimum like this one. It may not be the global minimum, but it's a really good minimum. That's what's unreasonable, right? Why? Why would that ever happen? What's different about deep networks that allows them to get there? And the answer is actually simpler than it looks at first thought. And the thing is that, again, this is with respect to the parameters, right? This is the parameters, and this is the error given the parameters. So as I modify the parameters, I have different errors, right? Now, this is not the parameters rule. This is just one parameter, right? So when I only have one parameter, what are the chances that I go down versus that I go up? About 50-50. Now let's say that I have two parameters, right? If I have two parameters, then if one goes down, the other one is 50-50 that goes up or down, right? If I have three, if one goes down, right, or say one goes up rather, I have 50-50 for this one going up. Let's say that it goes up, and then another 50-50 that the other one also goes up, so I'm down to 25%, right? The more parameters I add, the less likely is that all of them go up. And to define a minimum, all of them have to go up at some point, right? I have to reach a point where I have no escape. But if there is another parameter that is still going down, is still giving me a path towards some lower and lower minimum, right? So if I have 1 billion parameters that we've been talking about, what are the chances that all of them are pointing up at one point and I reach the minimum? They're almost zero, right? There's always going to be a way to go down. So the problem really is not in deep networks or in deep learning, is not being able to find the global minimum, but rather what the problem is, it's saddle points. And that's what we've been discussing in what makes learning difficult. This is not what interests us. We can assume that this function is always going down in some way through one or more of the parameters, but what I can find are areas of that function that are almost flat, right, for all the parameters. And what do we know about these almost flat areas, these saddle points? That the gradient is not good enough unless I increase my training rate like crazy at that point, right? I'm going to get a stack here. This is still not pointing anywhere, right? There is no gradient here or here. It's flat or almost flat. But I'm stuck here. There's no way out because I don't know which direction I have to go. That's the real problem in training deep networks, right? And how are you going to solve that? That's optimization, obviously. That's a problem in optimization. It's beyond what I'm going to teach here. But I'm going to give you some ideas of what people are doing to get around this problem, okay? So one of them that I've already mentioned, actually, when we talk about linear classifiers, is to add momentum. And this basically just means to consider that if I consider this instead of a point, I consider this a ball, right? I have a ball, right? A physical ball in this surface, right? And the ball moves in the direction of the gradient. But I consider the velocity of that ball as it moves down, right? The momentum that that ball has. And then if I consider this momentum, I could write, and you have this equations also in the slides for linear classifiers. When I mentioned this the first time, you could consider the velocity at time t plus 1 is equal to some rho parameter vt, right, the velocity time t, plus the gradient of your function, right? Say xt at time t, where xt plus 1 now it's equal to xt minus alpha vt plus 1, right? So when the ball rolls down, it reaches this point and then this minimum, right, this saddle point, and then because it has velocity, if it has enough velocity, it may be able to escape, right, through one of the dimensions that eventually is going to go down in a steeper way. And here, rho, it's called the friction. Okay? Meaning how much does the surface of the error function slow me down. Okay. There are extensions of this that are implemented in PyTorch and all the other softwares, or most of the softwares that Shanley mentioned in class, in the recitation. One of them is called Ada gradient, or Ada gradient. I'm not sure how people call it. The other one is RMS prop, and the other one is called Adam. I would recommend that I don't have much experience with how well Ada gradient works. I can tell you we tend to use Adam. Adam works really well. I would strongly recommend you try that. People swear by RMS prop. People say that this works really well. I have less experience with this, but it seems to work. So, between these two, I just tried them both. And, maybe try Ada gradient as well, but certainly these two. I would start with Adam if I were you, and then maybe try RMS prop. But the important thing also is to keep an eye on the literature. This is an active area of research, and it's going to develop tremendously in the next 2, 3, 4, 5 years. So I'm sure that more algorithms will pop out that are even better, right, at solving this problem of saddle points. So look for these implementations in PyTorch or whatever software you want to use. All right, 2 more things, and I'm done. Very quick things. Now, remember, was that like lecture 2, lecture 3, that we spent quite a bit of time talking about the average, right? How powerful the average is, right? That if you have multiple classifiers, you take the average of all these classifiers and more likely to be right than by just taking one of the outputs of one of the classifiers, right? And that if you have a group of people and you want to make a selection of something, or you want to make a guess on something, it's better than you all vote and then you compute the average, right? Remember that? This is actually quite often used in deep networks, especially if you participate in competitions where the testing data has been sequestered and you don't know what the testing data is. So there are multiple ways to do that. Number 1, train the network with different parameters, right? Until you can be sure that it works really well, but slightly different, right? And then let the network classify and take the average for the output, okay? If it's classification, you can take the majority vote. If it's regression, you can take the average, and so on, right? Another thing that you can do is train the same network with different mini batches, and then the output, you do the average of all these different trainings with different mini batches. And yet the third thing that you can do is, and this has become popular as the networks grow in size, is to, in these networks, to take this is output, but maybe here, you see here, I'm going to do another subnetwork here with maybe a fully connected layer here and call this y hat. And maybe here, I'm going to do another one and call it y tilde, right? And so on. So at different stages of the network, you create different outputs, different branches with different outputs. And then the output is going to be, again, the average or some type of combination of these different solutions. People are just trying to come up with ideas of how to go one step further, right? How to improve the outcome. And these are useful. The other one is called Dropout. Now, this is actually weird, but seems to help in training, especially. And therefore, it helps get slightly better results. So let me very briefly talk about this. So imagine that you have a graph like this. And I'm going to make a very simple graph, right? DAG, say that it looks something like this, okay? Okay, something like this. One way is to train this network as is, but the other one is to, at each iteration, drop some of these nodes out of the equation. So for example, I could drop this, and I may end up with, say, this network here instead, right? Right? So there are, oh, and this one then. So there are 3 nodes, or there were, that I've dropped out at this iteration, and then I train the network, and then I put them back, and I train with the network again with some other dropouts and so on, right? So I try different varieties of this, and you just have to select a percentage of the nodes that you want to drop out at each iteration, right? For example, if you drop out, say, 50%, which is 1/2, then you're going to have to be careful, because the different outputs that you get, right, will be multiplied by 2, right? Because every time that you do a specific dropout, so you have there are things that need to be addressed, but this seems to really work to facilitate training of the networks. The problem, obviously, it's a trivial problem. It takes forever to train these things, right? Because you just have to drop out a lot of nodes during different iterations. Okay, that's it. I'll see you next week. Have a happy Thanksgiving.